Welcome to the Deep Dive. We unpack complex ideas, pull out the surprising facts, and, well, give you a shortcut to being genuinely well-informed.
Today, we're tackling something pretty mind-bending, actually.
Yeah, think about this. What if you could capture someone's unique voice? Maybe, someone who's passed away, and let it speak again.
Or even just build a smart assistant that really gets you trained on your own digital chats.
It sounds like sci-fi, doesn't it? But today we're diving deep into how you can actually train your very own large language model, an LLM, basically from scratch.
Right. We're not talking about using some off-the-shelf AI. This is about building something that can mimic very specific communication styles, chat personally, or maybe even help preserve languages that don't get much attention online.
It's fascinating stuff.
Yeah.
So our mission today is to unpack that whole process step by step.
We'll cover everything, from getting your hands on the raw chat data, cleaning it up, figuring out the model's architecture, all the way to making it work with huge amounts of text.
Basically, your essential guide to understanding this really cutting-edge tech.
And for this deep dive, we're drawing heavily on a fantastic course by Aman Sodik. He breaks down this whole complex process really meticulously. We've sort of distilled the key takeaways for you.
Okay, so let's get into it. You've got this idea, a digital echo, a super personalized assistant. Where do you even start?
Well, all begins with the raw material, your personal chat data. Think WhatsApp, Telegram, Signal, that kind of thing.
So not just general internet stuff.
No, definitely not. This is about your specific interactions, the unique way you communicate.
Okay, but getting that data out.
Yeah.
I've tried exporting WhatsApp chats. It's not exactly a one-click download, is it?
Nah, no, not at all. It's a manual. You have to do it conversation by conversation.
Yeah.
And you end up with a pile of plain text files.
The TXT files, right?
Exactly. And they are messy, like really messy, full of links, those media-omitted tags, deleted message markers, email addresses, sometimes even those encryption notices.
So you can't just feed that digital garbage dump straight to an AI.
Definitely not. You need a cleaning crew. Basically, you use regular expressions. Think of them as super smart find and replace tools to filter out all that junk.
Okay, makes sense. Get rid of the noise.
Right. Once it's clean, you stitch all the messages together, concatenate them into one massive, continuous stream of text.
How big are we talking?
Well, for a typical personal data set, you could easily end up with, say, over 1.4 million characters of clean text, just from your own chats.
Wow. And this cleaning and prepping, it's not just theoretical, right? You mentioned preserving languages.
Oh, absolutely. Take Moroccan Darija, for instance. It's this amazing mix of French, Arabic, sometimes even numbers written out in the text.
Standard LLMs probably struggle with that.
They really do. They're trained on more, let's say, standard internet text. So if you train a custom model specifically on Darija chat data, you can actually build something that understands and speaks it properly. It helps bridge a gap.
That's a huge potential impact. Giving a voice to languages AI usually ignores.
It really is. So once you have that clean, long string of text, the next big step is tokenization.
Tokenization. Right. Converting text to numbers.
Yeah.
Because models don't read words like we do.
Exactly. They process numbers. Tokenization is basically teaching the machine its alphabet, turning your text into a sequence of unique numerical IDs or tokens. It's fundamental.
How do you choose the best way to do that? I mean, you could just turn every single letter into a number.
Right.
Character level.
You could, but the problem is you end up with incredibly long sequences of numbers, like super long. And that quickly fills up the model's context window. Its short-term memory, it can't handle it.
Okay, so that's not ideal. What about the other extreme? Making every whole word a token.
Word-level encoding. That makes your sequences really short, which sounds good, but then your vocabulary, the list of all possible tokens becomes gigantic, astronomically large sometimes. And that's really computationally expensive for the model to learn.
So too long is bad, too many is bad. What's the sweet spot?
The sweet spot, and what most people use, is something called byte pair encoding, or BPE.
BPE. Okay, how does that work?
Think of it like a smart compression tool for language. It scans your text and looks for the most common pairs of characters, or even short subwords like ing or the, or maybe common short words like the.
And then it merges them.
Exactly. It merges those frequent pairs into new single tokens. So instead of breaking running into 6 letters, it might learn run and ing are good, efficient tokens. It lets you control the vocabulary size, finding that balance between length and complexity.
Clever. And you mentioned special tokens too, like punctuation for the AI.
Yeah, that's crucial. You explicitly add tokens like start off text, end of text, maybe a separator token to show who's talking, and an unknown token for anything really weird it hasn't seen. These guide the model. They tell it where a message begins, where it ends, how the conversation flows.
Got it. So we've cleaned the data, turned it into numbers the AI understands using BPE.
Right.
Now building the actual brain, the
Yeah.
LL air architecture.
Right. And for what we're talking about generating text, learning from conversations, we mainly focus on one part of the standard transformer architecture, the decoder.
The decoder. Okay, what's inside that?
Well, a few key pieces. First, you have token embeddings and positional embeddings.
Embeddings. So those are like richer numerical representations, right? Not just simple IDs.
Exactly. They turn each token ID into a dense vector, a list of numbers that captures more meaning. And positional embeddings are vital because they tell the model the order of the words. Without that, dog bites man is the same as man bites dog, which, it isn't.
Yeah, definitely not. Okay, so embeddings give meaning and order. What's next? The famous part.
Ah, yes, the self-attention mechanism. This is really where the magic happens in modern LLMs.
How does it work? Why is it so special?
Well, older models struggled with long-range dependencies, understanding how words far apart in a sentence relate. Self-attention lets the model weigh the importance of all other words in the sequence when processing a single word. It can figure out that it in a sentence refers to a dog, mentioned way earlier. It allows for that deep contextual understanding.
So it can connect the dots across the whole sentence or even paragraph.
Pretty much. It helps the model focus on the relevant context no matter where it is. It's a fundamental breakthrough.
Okay, attention is the star. But there are supporting players, right? You mentioned things like residual connections.
Yeah, think of residual connections as like express lanes for information. They help the original input signal bypass some transformations, ensuring that the model doesn't forget crucial information as it goes through many layers. It helps with training stability.
And layer normalization.
Layer normalization helps keep the numbers flowing through the network in a stable range. It stops things from getting too big or too small, which can mess up the learning process. And then you have feed-forward layers, which add more computational power, helping the model learn more complex patterns in the data.
So these pieces, attention, feed-forward, normalization, they work together.
They do. They're usually bundled together into what's called a block. And the cool thing is this block is like a building block, a Lego brick. You can stack multiple blocks on top of each other to make the model deeper and more powerful.
More blocks, more power.
Generally, yes. More capacity to learn complex patterns. And then finally, right at the end, there's a prediction layer. This takes the model's internal complex understanding and converts it back into probabilities for what the next token in the sequence should be. That's how it generates text.
Okay, so when you're setting up a model, you're deciding things like how many blocks, how detailed the embeddings are.
Exactly. You're choosing parameters like block size, that's the maximum sequence length it can handle its context window again. Then embedding size, how much detail is packed into each token's vector. And the number of layers or blocks. A small starting model might have, say, around 12 million parameters in total.
12 million. Sounds like a lot, but I guess it's small in the LLM world.
Relatively, yes. The big ones have billions or even trillions. But 12 million is enough to start learning effectively from focused data.
Right, so architecture set. Now we actually train it, the pre-training phase.
This is where the learning happens. You take your tokenized data, split it into a training set for learning, and a validation set for checking progress. You use data loaders to feed this data to the model in manageable chunks or batches.
You said things like the learning rate, how fast it learns.
Yep, learning rate, batch size. And you constantly watch how well it's doing.
How do you feed it the data? Just randomly.
Well, there are two main ways. You can pick a random batch of data each time. That's usually faster. Or you can try to process all batches systematically. That's more thorough, ensures you see all the data eventually, but wow, can it be slow?
How slow are we talking?
For really big data sets, processing all batches could literally take thousands of days on a single machine. It's often just not practical. So you usually find a balance, maybe shuffle the data and iterate through it.
Okay, so it's training. How do you know if it's actually, learning properly?
You monitor the loss. That's a number that basically tells you how wrong the model's predictions are. You want the loss to go down.
What are the danger signs?
Well, you might see underfitting the loss plateaus. It just stops getting better. The model isn't complex enough or hasn't trained long enough.
Or the opposite?
Right, overfitting. This is tricky. It's when the training loss keeps going down, but the validation loss starts going back up. It means the model is basically memorizing the training data, including its noise, and it can't generalize to new examples it hasn't seen.
So ideally, both losses go down together.
Yeah, ideally both training and validation loss decrease, and there's only a small, stable gap between them. That's good training.
But you mentioned something unexpected about overfitting being okay sometimes.
Ah, yes. This is specifically for pre-training the base LLM. It sounds wrong, but a certain amount of what looks like overfitting can actually be good.
How so?
Because at this stage, you want the model to deeply learn the specific patterns and quirks of your language data. Like for Adrija, you want it to memorize how people use emojis for laughter or specific slang or the weird mix of languages. It shows it's capturing the essence of the data source.
So the goal isn't perfect conversation yet, just mastering the language structure.
Exactly. You want it to learn how to put words together correctly according to your specific data. We saw a model with about 13 million parameters get really good at this base language understanding, even if it seemed a bit overfit.
Okay, that makes sense. So pre-training gives it the language foundation, then comes fine-tuning to give it the specific skill or personality.
Precisely. The base model understands the language. Fine-tuning teaches it a task, like mimicking a person's style or being a helpful chatbot based on your conversation history.
Can you need a different data set for this?
Yes, a smaller but very high-quality structured data set. You format it carefully using those special tokens. Start off text, user, separator, the actual message, end off text. The key part is that the assistant role contains the examples of the output you want the model to generate.
And context matters here too, right?
Yep.
You mentioned no context versus with context.
Hugely important. If you just train it on single question-answer pairs, no context, the model might learn to give an answer and use the end-of-text token, but it often struggles with holding a real conversation. The answers might feel disconnected or irrelevant after a few turns.
So including the chat history is better.
Much better. Training with context, giving it multiple turns of the preceding conversation, significantly improves its ability to stay on topic, be coherent, and provide relevant responses. It learns to generate that end-of-text token much more appropriately right at the end of its intended reply within the flow.
Got it. And fine-tuning involves batches too. How do you handle conversations being different lengths?
Ah, good question. You use padding tokens. You basically add special blank tokens to the end of shorter sequences in a batch until they all match the length of the longest one.
So the computer can process them efficiently.
Exactly. It allows for efficient batching. And the clever part is you tell the model to completely ignore these padding tokens when it's calculating the loss. So they speed things up without interfering with the actual learning.
Smart. And you can get even more focused with masking.
Yes, masking the target. This is really useful for instruction fine-tuning. You can tell the model to ignore the user's part of the prompt or any instructions when calculating the loss. You only calculate the loss on the assistant's response part.
So it laser focuses on learning to generate the desired output.
Precisely. It becomes much more efficient at learning what to say in response. You use something called an ignore index in the loss function to achieve this.
Okay, so for the actual fine-tuning process, are there different ways to update the model?
Yeah, two main approaches. There's full fine-tuning, sometimes called instruction fine-tuning. This updates all the weights, all the parameters in the model. It gives you maximum flexibility, but it's computationally expensive, similar to pre-training and resource needs.
And the alternative?
The more popular and efficient method these days is parameter efficient fine-tuning, or PEFT. A common technique here is LoRa.
LoRa.
What does that do? It's quite clever. LoRa freezes most of the original base model's weights, like 99% or more of them. Then it adds a very small number of new trainable parameters into specific layers, often the attention layers.
So you're only training a tiny fraction of the parameters.
Exactly. This makes fine-tuning drastically faster and requires much less memory, much less powerful GPUs. You can often do LoRa fine-tuning even on consumer hardware. There's a parameter called rank that controls how many new parameters you add, giving you a dial to control the extent of the fine-tuning.
Wow, PEFT and LoRa sound like game changers for making this more accessible.
They really are. They lower the barrier to entry significantly.
Okay, but what if you do want to work with truly massive data sets? We talked about 1.4 million characters. But what about, say, 900 million characters? like that Atlas corpus.
Yeah, scaling up brings a whole new set of challenges. Just loading 900 million characters into memory might need 16 gigabytes of RAM or more. Your laptop might just say, nope.
And tokenizing that much data.
Could take ages. Remember, just 10 million characters took maybe 6 hours to tokenize. So 900 million. You do the math.
Yikes. So how do you handle that scale?
Smart tricks. For tokenization, you don't need the whole data set. Just train the tokenizer on a small representative sample, maybe 1% to 5%. It's usually good enough to capture the data distribution and saves a ton of time and memory.
And for storing those millions or billions of tokens.
Crucially, don't just save them as a standard pickle file in Python that tries to load everything into RAM at once. Disaster.
What's the alternative?
Use memory-mapped files. NumPy arrays, for example, can be memory-mapped. This means the file stays on your disk, and Python only loads the small chunks you actually need into RAM at any given moment. It keeps RAM usage super low, even with enormous data sets.
That sounds essential for big data. So you got your massive tokenized memory mapped data set. Can you train the model locally now?
On 900 million characters?
Right.
Probably not unless you have a supercomputer in your basement and a lot of patience. We estimated training a decent-sized model on that much data locally could take, well, maybe 77,000 hours on a good consumer GPU like an RTX 4070.
77,000 hours? That's like almost 9 years.
Exactly. It's just not feasible. This is where the cloud becomes absolutely necessary.
Renting GPUs from cloud providers.
Yep. Services like Lambda Labs, Google Colab Pro, or even free tiers on Colab or Kaggle, though those have time limits. Renting powerful cloud GPUs can take that training time down from years to maybe days or even just hours for really powerful setups. The cost is often well worth it.
Makes sense. Any tips for using cloud GPUs efficiently, since you're playing by the hour?
Definitely. Prepare everything beforehand. Do your data cleaning, tokenization, and preparation either locally or on cheaper, non-GPU cloud machines, VMs. Don't waste expensive GPU time on tasks that don't need a GPU. Have your code ready, your data uploaded. Minimize idle time.
What if the model is still too big for the GPU's memory, the VRAM, even in the cloud?
That's where gradient accumulation comes in. Let's say your ideal batch size is 64, but your GPU can only handle a batch size of 8. With gradient accumulation, you process a small batch of 8, calculate the changes, gradients needed for the model weights, but don't update the weights yet. You hold on to those gradients. Then you process the next batch of 8, calculate its gradients, and add them to the previous ones.
Accumulating them.
Exactly. You do this 8 times, 8 batches size 8, 64. Only then, after accumulating gradients for the equivalent of a full large batch, do you update the model's weights. It lets you simulate a larger batch size than your hardware technically allows. It's slower, but it lets you train bigger models.
That's another clever workaround.
Yes.
So after all this, cloud computing, memory mapping, maybe 40-odd hours of training,
Yeah.
what do you get?
You get a base model that has genuinely learned the structure and flow of your language data. For example, a 40 million parameter model trained on, say, 300 million tokens might not know everything about the world like GPT-4 does. It wasn't trained on the whole internet.
But it knows its specific domain.
It knows how to put words together coherently and correctly in the style of your training data. It's become remarkably proficient in that specific language or domain. And now it's truly ready for that efficient LoRa fine-tuning step to give it a specific personality or task focus.
What a journey. Seriously, from wrestling with messy WhatsApp texts to fine-tuning in the cloud, we've really covered the whole pipeline.
Yeah, cleaning the data, tokenizing it, building the transformer brain, pre-training the base language understanding, fine-tuning the personality, and figuring out how to scale it all up.
You really get a sense of the effort and the ingenuity that goes into making these AI tools we hear so much about.
It's complex, but hopefully we've shown it's not total magic. There are logical steps, clever techniques.
And the possibilities. They feel really personal now. Not just abstract AI, reviving voices like we said, or building assistants that just get you, or tools for specific communities preserving languages.
Exactly. It moves from being just this massive general AI thing to something you can potentially shape and use for very specific, meaningful purposes. It's becoming a practical skill set.
So the final thought for you listening. In this world flooded with generic AI, what unique voice, what specific knowledge, what personal conversation could you bring to life with a custom-trained LLM? What's waiting in your data?
The journey is definitely complex, but the tools and the knowledge are out there. We hope this deep dive has maybe sparked some ideas or at least given you the insights to explore this frontier a bit more yourself.
Thank you for watching. If you found this video helpful, don't forget to like, subscribe, and hit the notification bell so you never miss our future lessons. See you in the next video.